Greetings, this is Eugene the Philosopher, the greatest living philosopher after the unfortunate passing of Quentin Robert de Nameland, who has been the greatest living philosopher before me. Now, on this channel, you've probably heard many a time when I say that, oh, the networks of culture, oh, the networks of ideas, blah, 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 like networks of power, etc., etc. And you may have thought, like, well, how is it related to actual science? Like, maybe, Eugene, you are a bit delusional, right? So you live in a world of dreams or of abstractions and some irrelevant stuff and such, right? So, the purpose of this video is exactly that, to sort of show you how it works in practice, how an actual scientific experiment is drawing its power from all these cultural / political / scientific networks of ideas, ultimately cultural networks, right? And as an example, I took the double-slit experiment, and I'll probably not describe it to you here at the very least. Maybe I'll just give you a link to my other video where I explain it in much more detail, but we'll see how it goes. So, in this video, I wish to show you the very, very, very reduced, like bare bones type of network that is actually supporting the experiment, alright? So this is the purpose of this video. Like, sort of the objectives of this video are to, well, again, firstly, and this is the main objective, to demonstrate my points about the networks of ideas, networks of science, politics, and culture in practice on this example, right? But there are also secondary objectives, like one of them is that to show you that, again, to reinforce my previous points from some of my previous videos, like one of the points I made many a time is that, none of the experiment, like the experiment is never truly raw, if you know what I mean. Like, but any experiment is always based on a theory, and not only a single theory, but most likely multiple theories simultaneously, and a crap ton of ideas in general, right? So it is a very big delusion, I believe, of certain people who say that, oh, it's too many theories today, like we need raw data. Well, guess what? There's no raw data. Like, any data only comes with a huge baggage, so to speak, right? Behind it, package, so to speak, huge package, if you know what I mean. So any experiment is based on multiple theories and ideas tied to very deep layers of culture, and with all of their possible misconceptions. So we may trace many of religious, moralistic, aesthetic ideas, even in scientific experiments. Like, it sounds wild, but if you analyze the scientific experiments, scientific theories, you would see how actually they feed off of those remote, seemingly remote areas of culture, right? Again, maybe I'll mention it later in this video when we'll talk about the actual thing, but just right off the bat, I can say that, again, the idea that mathematics governs the world is a religious idea fundamentally, because Francis Bacon said that, right? He said that the God created the world and he kind of wrote the world in the language of mathematics. So why is mathematics applicable to the description of the world is because it's guaranteed by God, right? So if you remove the God, how can we apply mathematics to describe the world? The question remains, I should say. So any scientist scientist, singular, who believes that mathematics is some sort of a sacred language that the world is written on is basically a crypto believer, you know, in a God. I mean, that's one point. I mean, that the experiment is never raw, right? There's always a bunch of theories standing behind it, hiding in the bushes somewhere. And the second point, like the secondary objective, would be that to show of this video, I mean, is to show how a small, seemingly remote and irrelevant idea seemingly like throws huge tsunamis or avalanches throughout the whole culture, and can manifest in various other forms elsewhere, right? So even in such clean, sterile, and I don't know, objective, again in air quotes, areas such as science, right? So yeah, I firmly believe that the world is driven by ideas, that ideas are immortal, and ideas are a really cool thing. It's like a work of art, but the kind of work of art that resonates with everyone, if you know what I mean, or at least a lot of people. So some dude may have come up with some idea like 10,000 years ago, and we're still reaping the harvest of it, whether it's good or bad today, which is the case on many occasions, I would claim. All right. Well, I think that's all for the introduction, so let's get started.
Alright, so here's a scheme I produced specifically for this video, and as you can see right away, it's a little bit chaotic maybe, and so like a few caveats right from the start. So it's already a bit chaotic, as I've said, and therefore I've actually omitted some of the things. Like some of the things I may have forgotten, some of the things I may have omitted deliberately, like some of the obvious connections that should be present are not, like the connections between quantum mechanics and, let's say, the notion of a number, the notion of a wave, etc., etc. Like the whole purpose here is just to illustrate, right? It's not to give you a full network, if you like, of ideas, etc., etc., but it's more like an example, right? So we're dealing with like bare bones type of things right here. So our core, okay, that was one caveat, that some of the things are not present. The second caveat is that there is actually an extra layer to all of this. Like here, I've only depicted like the scientific part of the network, whereas there is also a political part of the network. If you like, you may treat it as like an extra dimension. So this is only a layer, right? And there is like layers of politics below and above of this, like in 3 dimensions, where we'll have like a political power of various laboratories, of various like scientific committees, like the Nobel Prize Committee, obviously, etc., like political power of various scientists who support all of this, etc., etc. So this is also not present here. I'm only dealing with the ideas kind of layer here. Okay, and there was some other caveat that I've even forgotten, but whatever, I guess. Maybe I can remember it. No, I cannot. Okay, let's proceed then. So our core node is the experiment right here, even though it doesn't look very important, but still it's the most important part of this picture. And the double slit experiment, by the way, I'll give you links where I describe the experiment in much more detail in my lecture about quantum mechanics, because again, it would be just an overkill to do it here as well. So the experiment, I've only like limited it to a simple statement that when both slits are open, we observe interference pattern. But there's obviously a second part to it, like when we close one slit, etc., the pattern disappears, etc., etc. And by the way, I've also now remembered that it's actually, you can also argue that it can be, like from it follows Feynman's path integral approach, which also is very important to particle physics, but I just forgot to include it here. But whatever. And so all of this supports this experiment, right? It's what it's made. I don't know, like you can consider the experiment as being the focal point of these things, right? So without these things, this experiment is impossible. Like you cannot make this statement at all, right? So again, reinforcing my previous point about the baggage that any experiment comes up with, or comes with in the first place. So let's start considering all of these nodes of the network and to see if we can comment on some of those. So here, like this more or less separate block is dealing with statistics and is dealing with how we detect particles, how we make claims about our detection of particles. So the first node that feeds into the experiment is that the detector can recognize individual particles, right? It's a very strong statement if you think about it. Like, and it is reinforced in its own turn by the detector structure, like its makeup, like how do we build this detector, what it's made of, like in particular it may be built of photoelectric multipliers, etc., etc. And there's obviously a whole supportive network behind these devices, right? So we know they work, no in air quotes, obviously, etc., etc. So there's a big supportive network behind this thing and behind the detector structure, because we think we built it like in a bona fide type of manner, right? We think it works, etc., etc. Therefore, we can claim that the detector can recognize individual particles after all. Then we need statistical part, because if we shoot particles one by one, obviously these are kind of unrelated particles, you might say. But at the same time, the ergodic hypothesis, which is again a hypothesis, it's a principle, it cannot be proven by definition. It states that the average over time in one ensemble is equal to average over multiple ensembles of the same sort. That might sound a bit difficult to understand, but basically what it says is that we can observe one ensemble, one statistical ensemble over time, and it would look the same as if we took the average over multiple copies of the same ensemble, like kind of multiplied in space, if you know what I mean. Like if we take one vial with some liquid, it would over time behave in the same manner as 1,000 copies of this vial behave, the average of 1,000 copies behave right now, sort of. I'm kind of simplifying, and actually I don't really do much justice to it, but hopefully it's understandable. So why do we need that? Well, it's because we have individual particles that we then sum into a single statistics, right? Into a single statistical set of data. So we kind of claim that these particles are actually related in some very fundamental sense, that they are part of the same ensemble, right? So this is why we need that here. And by the way, like half or even more of thermodynamics and like statistical mechanics rests on ergodic hypothesis, even though, as I've said already, it cannot be proven. So this is one of the weakest points of thermodynamics in the first place, where like if you wish to conduct some sort of serious criticism of thermodynamics, then you need to look into it, certainly. Okay, then we have independence of separate experiments feeding into it, which basically means that if we measure a position of an electron, let's say right now, and another electron a minute later, those measurements would not interfere with each other in any way, right? So we have to assume certain linearity of interactions. Like if you look at my video, Nonlinearities in Time, I talk there specifically about this phenomenon where your system might actually be modified by one of these measurements, for example. And then the next measurement you make would no longer be unaffected, if you like, by the previous measurement. So this is a thing we need to keep in mind. But here we just assume all of this is true, right, in this experiment. Okay, fair enough, why not? We've dealt with this block so far. So this block is mostly about waves, like because again the statement is that we observe interference pattern, and therefore we need to know what interference is. So here we have, let's consider this arrow, for example. We have interference plus the Huygens principle. So the principle is about how waves propagate, right? So it states that, let's say we have a spherical wave and it's like expanding, right? And the principle states that each point that the wavefront have reached itself becomes a source of secondary waves. So if you look at the spherical wavefront, each point of its surface would become the source of the next, like a spherical wave. And then the interference of these waves would produce the picture that you observe in the end, like the picture of the wave propagation itself, right? But we also need interference in the first place, right? And how do we arrive at the concept of interference? Well, we need to have coherent sources. And, well, okay, I wouldn't give you a definition, but, well, basically it means that the two sources, in our case, those would be two slits that the wavefront of the particle have reached, right? So since it was a single particle, then we can claim that these slits would act as a coherent sources, which means that you would have a constant displacement of phase. So we need a concept of phase as well, right? And the concept of phase cannot be reached without the notion of a number, or I don't know if I'm using the word notion in the correct manner here. It could be like idea or concept of a number. Those are synonyms in my eyes, at least for the sake of this video. So we need a concept of phase to know about coherent sources, and the interference can only exist for coherent sources. So that's why all of this is justified. At least we assume it is, right? And then we need a notion of a wave in the first place to arrive at the phase concept, right? And how do we arrive at the notion of a wave? Well, we need a notion of a cycle, that something repeats itself, which means we need a concept of identical objects, because if something repeated itself, it means it was the same thing, right? Just in the next moment in time. So we need a concept of identical objects, and we need the concept of separate objects first, because, well, this other object is not the same as the previous one, yet it still is identical to it, right? The next moment in time is different, yet we have the same sort of oscillation in it, if you like. And how do we arrive at the concept of separate objects? Well, we need sensory organs for that. We observe the world, we see that there are different objects, and yeah, we just conclude that. And we need the notion of change as well to arrive at the concept of a wave. Let's say the wave looks at t plus delta t differently rather than at just the time t, right? So yeah, but you also have to have the notion of a cycle in order to in order to allow the wave to repeat itself in some sense. But then we arrive at the notion of a wave, and everything is hunky-dory pretty much from here, right? Okay, we've pretty much dealt with this segment. It was actually surprisingly quick, I would say. Another thing we need is the concept of, it's actually a principle, that identical particles are indistinguishable in quantum mechanics. So let's say you cannot make any distinction between two different electrons, even though you know they are different, but they're kind of the same at the same time. Which, by the way, brought forth this concept of a one electron universe. If you may have heard about that, I think it was Feynman or maybe Wheeler who arrived at it, but it's again, it's a separate concept. I wouldn't discuss it here. Why do we need that? Well, to help this part. Like, we say that we can arrive at statistics of, let's say, electrons hitting our detector because electrons are ultimately the same, right? So again, there is some intimate connection between all of them, wherein we can claim that they are actually a part of the same statistical ensemble, etc. All right, what else do we have here? Okay, we'll probably go into this part, and it's actually the most interesting part, I would claim, of this whole scheme, because it's a part where you can actually clearly see how the network is actually sort of negotiating with itself. Like, you see, the problem is, we have this statement that the screen is impenetrable to particles, right? And it's very important for the experiment. I mean, the screen where we have our slits. We just assume that the particles cannot go through the screen, right? And therefore, all of this, machinery starts working. Whereas the quantum mechanics itself states that there is such a thing called tunneling effect, where basically quantum particles, like any particles really, can tunnel through the barrier. And in some sense, there are no impenetrable barriers in quantum mechanics. So this thing actually counteracts this very crucial point for our experiment, and it kind of sabotages the experiment in the first place, right? Whereas we just make a naive claim here that impenetrable objects exist based on our sensory experience, right? We have, I don't know, stones, I don't know, whatever, ground, which doesn't seem to be, we doesn't seem to be able to penetrate, and therefore we arrive at this simple intuition that there are impenetrable objects, the particular case of which is our screen, right? But quantum mechanics negates that. It says, no, there's no such thing as an impenetrable object. So our particles can tunnel through the screen and screw up our whole experiment, right? And the funniest thing is that quantum mechanics itself is supported by this experiment, right? So we arrive at this kind of sickly loop where it kind of is destroying itself, right? Which is kind of funny. But what we also have in science is method of analysis. So basically the experiment, what it has to do here is to somehow negate this negation, if you like. It needs to draw support from some other networks that would say, okay, tunneling effect is not a factor in our experiment. So we need this supportive network. And here it is. It's the method of analysis and the perturbation theory. Now, I kind of screwed it up a little bit because it's not perturbation theory per se, but they are very related. So I decided, what the hell, I'm going to include it anyway. So what method of analysis says? It's one of the logical / scientific methods. It says that in order to deal with a problem, we need to separate it into parts, right? That's analysis. Synthesis would be the reverse process. We kind of join parts together. But analysis says in order to figure out the problem, you need to separate it into parts. And even more importantly, or rather, that would be a prerequisite for you to determining which parts are important and which are not. And then you can just discard the unimportant parts and just consider the important ones. And then you'll be able to deal with the problem effectively, right? So because you would reduce the number of unknowns significantly. And perturbation theory is kind of about that. I've actually talked about it, I think in that same video about nonlinearities, but I might be wrong. Maybe it was some other video. But I'm too lazy to actually find it out which one it was. But anyway, so analysis says in connection to this problem, well, how important is the tunneling effect here? And you can make a claim that if you make a screen thick enough, let's say, so that tunneling would be very small, like there would be a very small probability of tunneling, then you can discard it. So this is a huge helping hand. By the way, probably I need to make a comment. Like perturbation theory, it states that, again, in order to deal with a problem, you need to find a big contributing factor and a small contributing factor. Again, I gave you the examples of, and then you can use all the machinery of Taylor series and things like that, and the problem will become very easy to solve because it's a polynomial series, which is, again, pretty easy to deal with current mathematical apparatus. So I gave you the examples of tides, like what influences. Of course, it's a spoiled example because tides aren't actually that simple to deal with, like tidal waves, I mean. So we have a big contributing factor of Earth's gravity, and we have a smaller one with like lunar gravity or solar, right? And we include these smaller contributions as like what is called the first order correction to Earth's gravity. And it describes pretty much the effect completely, even though it doesn't, as I've already said. But I mean, we'll use it as a proxy. We'll say it works, even though it actually doesn't. But whatever. So yeah, so we have this supportive network, brought forth by the experiment as if it was something almost sentient, to support the statement that the screen is actually impenetrable. Like, it is penetrable, as tunneling effect claims, yet not to such a degree as to sabotage the experiment, right? So analysis helps us to say, well, it's actually a small effect, it doesn't matter. Even though it can happen, it's not a big issue for us, right? So there it is. I think I've pretty much talked about all of it. But again, this is only a scientific dimension to all of this problem. But just appreciate how much of stuff is included there, right? Even a very, very, very remote, very, I don't know, simplistic ideas such as impenetrable objects do exist. They are absolutely vital. They are necessary for the experiment, well, in particular this statement, to happen, to appear, to be true in some remote sense at least. Then again, there are many supportive networks which have excluded, again, speaking about the engineering behind the detector, let's say, engineering behind the screen, you might also claim. Like, it's not just any screen, it should be made specifically for this purpose to be impenetrable to particles, so you need to put some work into that as well, etc., etc. So pretty much any node here can be dissolved into a huge network in its own right? So yeah. But other than that, well, hopefully it was a useful illustration. Hopefully, I don't know, at least you've got a general feeling of what I'm talking about when I'm talking about like the supportive networks of theories and experiments. Like again, you see, experiment. You could have said, well, it's just the raw data. Well, it's not just raw data, as you can see, right? It's very far from being that, in fact. Like, you have a ergodic hypothesis, which is a hypothesis, it's a principle, it's an axiom, it's unprovable in principle. Tautology, excuse me for that. And you claim you have raw data right here. No, you don't. You have all these hidden implicit principles, all these hidden implicit, like, half-intuitive concepts appearing here and there, and even more complicated concepts like quantum mechanics actually acting against you. Yet you still manage to work through that thanks to the supportive networks that you have, right? The defensive mechanisms, so to speak. All right, I think that will be all.
Thank you for watching. The eons are closing.